Oh, thanks for the kind introduction, and thanks. I would like to thank the organizer for having me here. So I'll talk about gravitational waves coming from quasi-stable string network and its implication in recent pulsar timing array data. And I'll talk about a realistic model based on SO10 where we can get super heavy quasi-stable cosmic string which can explain the pulsar timing array data. So this talk will be based on our work in collaboration with people like George Lazarus and Kaiser Safi. So let's get started. So here is a brief outline of my talk. So I'll start from an introduction of grand unified theories beyond the standard model and formation of topological defects, radiation of gravitational waves, and various kind of constant coming from the topological defects. Then I will talk about a grand unified model based on SO10, its symmetry breaking chain, and the formation of monopole strings and their composite structures. Then I will talk about the formation of quasi-stable cosmic strings, its gravitational wave background, and its implication in the recent evidence of gravitational wave in the pulsar timing array data. Then I will talk about the unification solution in this model, and I'll finally summarize my talk. So here is a schematic view of a grand unified theories. All we know that the standard model is based on a gauge theory, where the strongly interacting quarks transform as a fundamental representation under an SU3C group. In electric sector, we gauge basically left-handed chirality, so that all the left-handed fermions transform as a fundamental representation under this SU12 group, and we impose some phenomenological charges we call the hypercharge to each multiplets. Here we are gauging the chirality, so for each fermion the theory becomes anomalous at the quantum level. However, the quantum number of all multiplets are such that this quantum anomaly cancels among themselves miraculously. The basic idea in a grand unified theory is that the standard model is a low energy artifact of a unified theory at a very high energy. In between them, there could be some possible scale associated with some possible intermediate gauge symmetry, and there will be some scalars whose vacuum expectation value will spontaneously break any higher symmetry to its daughter symmetry. Now there are several examples of grand unified theories. The minimal example is based on SU5, which has rank 5, same as the standard model. In this model, all the standard model fermions are unified into two representations, 5 plus 10, and this combination in fact cancels the chiral anomaly because SU5 is the SUN group, so it has anomaly. Next model is based on anomaly-free group SO10. It has one rank higher. The interesting thing is that here all the standard model fermion, including a left-handed anti-neutrino, can be included into one's primordial representation 16. And this model naturally gives rise to a seesaw scale at the intermediate scale around 10 to 12 GeV. There are other models where based on higher rank group, which predicts some exotic fermions, vector-like fermions, sterile neutrino-like fermion, along with the standard model and right-handed neutrino. Now, during the spontaneous symmetry breaking of any parent group G to its daughter subgroup H, topological defects may be formed. In brute force mathematical language, the non-trivial homotopy group of the vacuum manifold, which is given by the coset of the daughter symmetry in its parent symmetry, implies the formation of topological defects. Various kinds of topological defects can be formed, namely domain walls, cosmic string, monopoles. For example, in a simplest model, when you break SUN to its one of the diagonal generator, we call it U1x, we get monopoles. When this U1 is broken to some of its subgroup or its two identity, we get strings and so on. And as we Professor Vajraspati talked, the breaking of any discrete group eventually gives rise to the formation of domain one. Strings is especially interesting. It's a one-dimensional object. It's basically the false vacuum trapped within the ground state of the true vacuum, and it is stable because of the topology around its. So it has some topological charge, so it cannot decay. And this strings has very nice property. This strings has string tension which is proportional to the square of the vacuum expectation value that form the cosmic string, and And there have been like lot of studies, mostly based on like these local strings. This formula is for local strings. So they can intercommute, form loops, and radiate gravitational, and their evolution of this network enters a scaling regime. Scaling regime is a kind of self-similar attractor kind of solution. If you take in the time regime, if you take two different batches of time, the network looks exactly same. And during the scaling regime, the energy density of this network becomes a fraction of the critical energy density of the universe, and it's a tiny fraction, g times mu. That's why it can never dominate the universe. So unlike dominal strings can never dominate the universe. So it's not pathological. Now these strings can form loops, and these loops can decay, and the power is given by this kind of quadrupolar formula. I'm not going into the details of all the mathematical stuffs. So here let's look at the frequency. The frequency is inversely proportional to the loop length, and the loop length is proportional to the time when it produced. So the large loop produced at the late time, and smaller loops produced at the earlier time, and the frequency is inversely proportional to that. So the frequency, the higher frequency will be contributed from the smaller loops that form in the early universe, and the lower frequency will be contributed from the larger loops which can be formed in the late universe. With this, we can understand the anatomy of a total gravitational wave spectra. So it has different parts. Like there is a scale invariant part, which comes from the string loops that form and decay during the early radiation dominated universe. It has a lower cutoff, frequency cutoff, which depends on the time scale of the time scale of the radiation domination, which we take the eco-density time or TEQ, and there could be a higher frequency cutoff which depends on the formation time of the string network. Here we have taken some time scale after which the string doesn't suffer any friction domination. And in the low frequency part, there is this peak kind of structure which comes from loops that form during radiation dominated universe but decay during matter dominated universe. There could be another subdominant peaked spectra which comes from loops form and decay during matter dominated universe. This is possible because I have taken g mu 10 to the minus 9. So the time scale of decay is greater than the equidensity time. So this kind of structure can be formed for this. G mu 10 to the minus 9. So this is basically proportional to the square of the vacuum expectation value divided by the Planck scale whole square. So it's 10 to the minus 9 is 10 to the 14. 14 GeV. Yeah, that is 10 to the minus 7 for stable cosmic strings. Yeah, for stable cosmic string that exists till the CMB. Now there are various kind of constant like stable domain wall contradicts the standard cosmology, so they're pathological. There is an upper bound, like we haven't seen any monopole. So there is an upper bound on the monopole flux, which can be converted into the so-called the co-moving number density, which is roughly around 10 to the minus 27. It's like all kind of like macro gives bound on the non-relativistic, ice cube gives bound on the relativistic monopole. So all gives kind of this kind of value, boils down to this kind of value. There is a CMB constant coming from the stable strings. Like earlier days, people used to think like the structure formation is due to like it's seeded by the cosmic string, but that is not. So in turns, this CMB observation gives a constant that G mu should be less than 10 to the minus 7. Also, the LIGO-Virgo run-3 data gives a constant on the like similar constant, and this constant come around the decahertz frequency of the gravitational wave spectra. This frequency range is important because decahertz is high frequency, so this is associated with the early universe. Also, PTA experiment put a constant on stable cosmic strings like G mu 10 to the minus 10 around the nanohertz frequencies. PTA has found evidence of gravitational wave which can explain by metastable cosmic strings, but it gives a constant on the stable cosmic strings 10 to the minus 10. This is roughly around 10 to the 14 GeV or so. We consider a symmetry breaking pattern where you start from a SON or spin-10 group, which is broken to the Patisalam, where we unify the quark lepton in a SU4 group. And in the next step, this can be achieved with a 210 dimensional scalar. There is another scalar which is contains the adjoints of this Patisalam SU4 and SU2. If we give the wave to this component, this SU4 will be broken to SU3C plus U1B minus L, and SU2 will be broken down to its diagonal generator. Then we give wave to the neutrino-like right-handed neutrino-like component of a 16-dimensional X. So this is this is an alternative way at some scale MR, and this breaks this U1B minus L and U1R to the hypercharge 1Y. Now, when we break SU4 to SU3C with a remnant U1B minus L, this produces a monopole with magnetic fluxes associated with the unbroken U1B minus L, and there could be some confined color magnetic flux as well. And altogether, we can define this generator for the associated with the flux. Like 1 to 5 rotation along this generator basically gives the formation of this monopole. And similarly, the breaking of SU2 to its U1 subgroup generates monopole. We label it as blue monopole. This is just name. The like this winding monopole is labeled as red, and this is so. This is a name given by Lazarus and Safia. I am using the same name. So this is nothing to do it. Like just to understand the stuff. Now, when this in the next breaking, when this U1R and U1B minus L is broken to U1Y, this produce this is a broken generator, and this produce cosmic string. But these cosmic strings are not topologically stable. They basically connect a monopole to its anti-monopole, and there is another possible structure where this monopole is connected to a blue monopole by the same cosmic string. And as they and because this kind of structure oscillates, they eventually collapse, and when they collapse, they produce a monopoles with 2 units of Dirac charges. This is sometimes called the Schwinger monopole. So this the main point is that in this symmetry breaking pattern, we get some structure where monopoles gets connected by a string, and this the net topological charges of this kind of structure is 0, but this structure are very important because they can give rise to the formation of quasi-stable strings. These are unstable structure. Now, in the formation of we consider, let's say, magnetic monopoles created prior to the cosmic strings. They experience partial inflation. They experience some part of, let's say, some e-foldings of the during the inflation. And after that, when the strings form, they make random walk with the step of the horizon of particle size of the particle horizon, and they form a network of a stable cosmic string before the horizontality of the monopoles. Because we get a network of stable strings, these strings can intercommute from loops which will eventually decay into gravitational waves, and the frequency, as I have earlier mentioned, is inversely proportional to the length of the loops. Now, as the monopoles re-enter the horizon at some cosmic time Tm, we obtain monopole connected by string segments, which is unstable and will eventually decay. So in this case, what happened, because the large string loops greater than the particle horizon, size of the particle horizon are absent in this case, there will be the gravitational spectra in the low frequency region will be absent. So we'll give, so in case of stable, we get a low frequency region, but here we cannot get a low frequency region. So there is a cutoff at the lower frequency range. And the gravitational is contributed from like loops that formed before this horizontality, and decays loops that forms before this horizontality of the monopoles, but decay after this time scale, and we get a total background. Now, there have been a lot of talk by this for this gravitational wave. So there have been an evidence of gravitational waves in especially the NANO-Grav data, strong evidence, which can be mergers of supermassive black hole binaries. But there are some cosmological models or new physics model which have some strong base factor over these supermassive black hole binaries, but they are not like clear evidence or discovery that they are preferred, but they have stronger base factor over the minimal model of supermassive black hole binaries. And one model is the metastable string and cosmic superstring. In our case, this if we see the quasi-stable cosmic string, they are also very good in explaining the NANO-Grav data. And sorry, I haven't mentioned the, so it has base factor around 50, so that is comparable with the metastable strings or other cosmic superstring. And the value of G mu is around 10 to the minus 7 to 10 to the minus 5. This is near Guth scale or Guth scale, associated with near Guth scale and Guth scale. And such kind of G mu can be obtained in supersymmetric theory easily, because supersymmetric gauge couplings like tend to meet at unification scale. Instead, we give we construct a non-supersymmetric model, because there is a 2 abelian group in the intermediate scale which can mix. But because these abelian groups comes from non-abelian symmetry, so at the unification scale there is no mixing. But we consider a dimension 5 operator suppressed by some cutoff scale, and this contains this component of 210 dimension containing the adjoints of the subgroups of the Pathi-Salam subgroup. This is under 4 SU4C, this is under SU2R. And this gives rise to a mixing term at the Guth scale when this component gets a wave at the Guth scale. So this induces an epsilon order of mu divided by lambda. Now we do the follow the simple mathematical tools, like we solve the RG and everything. And here is the matching condition. When we match this U1 gauge coupling with this off-diagonal term with the hypercharge, you see there is in the numerator there is a term with minus sign, which in turn reduce the value of 1 over GY square or 1 over alpha. So this is very important. If we see the running of the standard model gauge coupling in non-supersymmetric theory, the SU3C and SU12 can mate, but this alpha Y cannot. It has some lower value. So our proposal is that due to this U1 mixing, this off-diagonal term, which is induced by the higher dimensional operator, actually at the Guth scale makes an effective coupling which is lower than the usually from the usual unified coupling, and this helps you to achieve the unification solution. And the intermediate scale, you can see it's near the Guth scale, around 10 to the 15 to 10 to the 16 GeV. And what we found that unification occurs for epsilon order of 0.1. So in principle, like this, because this kind of high dimensional operator can be induced by some theory of gravity, unknown theory of gravity. We expect this should be the Planck scale, but instead we are getting some epsilon to such value that this lambda is lying between the Guth scale 10 to the 16 to 10 and the Planck scale. So it's kind of some kind of weak gravity scale. And if we see the solution region, this predicts G mu around 10 to the minus 7 to 10 to the minus 5, which is at the right value. And also it generates the seesaw scale around 10 to the 14. And all this thing is like suitable for reproducing all the standard model, all the electric observable, including the neutrino mixing and other parameters. And this G mu is suitable for explaining the gravitational waves signal in the pulsar timing array data. So this U1 extra U1 coming from yeah, it's coming. It's a subgroup of SO10, so it's there.
Is subgroup or is it extra U1?
No, it's subgroup of SO10. It has rank 5, so you can have extra diagonal generator there. So here is a summary. So I'd like to leave for the audience. Thank you.
Larger than 10 to the power minus 7 is
No, this is
allowed.
unstable.
Sorry,
Okay, so sorry. So this horizon reality time scale is 10 square second. So it is much before the TR CMB. So it is not pathological for the CMB observation. CMB is much later.
But it can produce also very relativistic particles. So
yeah, but that will not impact anything.
okay.
So I have one question. So how going to scaling regime actually help you to get rid of this cosmological catastrophe that you know that if they don't go to scaling regime, then your total energy budget will be captured by these cosmic strings. So how it actually helps? So it's going to scaling regime. So then what actually happened? As you know that radiation actually scales like energy density 1 by a to the power 4, matter 1 by a cube, and their energy density scales as 1 by a square. So
1 by
cosmic string
1 by t square. So it's like
I think
so 1 by t square. So it's matter and radiation. It's same, right? 1 over t square.
no,
Sorry, 1 over t square. For matter and radiation, it's always 1 over t square.
and what about cosmic strings? They also 1 by t square.
1 over t square, but it's a tiny fraction of the critical energy density. Critical energy density is 1 over g, and it is mu over by t square. So the ratio is g is proportional to g times mu. So
all are scaling as 1 by t square.
Yes.
Matter, radiation, and cosmic string.
And it's a very tiny fraction. G mu is 10 to the minus 9, 10 to the minus.
Another question. So in I think slide number 3 or 4. So you have shown this. Yes, the previous one. So not this. Go to previous one. So you have yes. So you have shown this non-trivial homotropy group pi km. So what is the condition to form cosmic strings on this pi km?
Okay, this pi 1 should be like pi 1 of the vacuum manifold would be non-trivial. Like pi 1, if you break U1 symmetry, so your vacuum is basically an S1. Pi 1 of S1 is integer values like Z. So that gives you cosmic strings. And this integer value is also proportional to the winding or the topological charge of cosmic strings.
Thank you.
You showed some results from PTAs. You went with the NANO-Grav data, and I kind of understand why. But I was just wondering, the EPTA and the PPTA have longer data span.
Yeah.
EPTA in particular sets a much stronger limit on the metastable string.
Okay.
Much stronger. If 10.6 is much stronger than 10, then yes.
Sorry, for metastable string?
Yes, because
for cosmic string, I think.
cosmic
Stable, they consider stable cosmic string. Yeah.
Yes. So we have a slightly stronger limit elsewhere, and even
Yeah, this is I use the older version, so.
sure. As I said, I understand why, but I'm wondering if it would make a difference to your calculation if you did use.
Yeah. Till now I used only NANO-Grav data because they have a big collaboration for new physics and other stuff.
We also have
Yeah.
big collaboration.
But yeah. I'll from next time I'm using PPT as well. Yeah, and other data as well available.
Because I would be interested in how big effect it has on calculation.
Yeah. This here I have used NANO-Grav data only.
But the advantage is you switch to almost twice lower in frequency. And from those constraints, it's hard to see. But the other PTAs do get more
Yeah.
at the lowest frequency. But then all PTAs are basically crippled because our most constraining data set
Yeah. Sure.
Okay, so one last question.
Stupid questions. Could you comment on constraints from proton decay? Or
Yeah, proton decay.
other constraints. So this model is still safe. From
Yeah, yes, it's much like we have a small region is ruled out by proton decay. There is a region which can be observed in the next
So
generation.
how can I read this? Sorry, how can I read this plot?
Yeah, this can be like this can be translated into proton lifetime. Sorry, I haven't explained it. So this is the unification scale, and this is the values of the coupling. So this is not important. The unification scale is important. So high superconductor has ruled out kind of 10 to the 5 times 10 to the 15 GeV or something of the guard scale, and it can probe till like 8 times 10 to the power 15 GeV till in the hyperconductor in the next generation. But in our model, it predicts a larger, in the most of the case, a larger value of MU.
Oh, okay, that's okay. That's your parameter.
Yeah, it's actually no,
Okay,
it
thank you.
cannot
Thank you
reach
very
that
much.
sensitivity.
Okay, I think we are running out of time. So Rinku, thank you for the nice talk.